Energy sources of most of the objects in the universe are actually nuclear reactions. And therefore, we have to understand nuclear physics if we want to understand the cosmos. And if we also are interested in the specific question how elements are being formed, what the origin of the elements in the universe, and therefore also our own origin is, we have to understand the nuclear physics, and we have then to model all the objects in the universe, our own galaxy, the sun, and so on, to understand this. And this has come actually a long way in the last 50, 60 years. We now have a good understanding. We would know how gold is being formed. We know how carbon and oxygen is being made in the universe. And carbon and oxygen, of course, is the basic building block of life. And therefore, we come back to the simple question where we are coming from. A star creates heavier elements during its lifetime. So for the 10 billion years our sun is living, or the several million years a heavier star is living, they actually use the trick that they combine lighter nuclei starting with hydrogen to heavier one up to nuclei like iron. But of course this doesn't help us too much, because this happens in the center of a star. And for us to being built out of these elements, these elements have to get out of the center of the star, and this happens in spectacular events called supernovae, where these stars become unstable in the center under its own gravity because they lose the nuclear energy source, and then gravity wins, the inner center collapses, and the gravitational binding energy is released and can explode most of the star, and in this way also the elements are blown into the interstellar medium, and then finally we human beings can be formed out of that. A few seconds ago we discussed the production of heavy elements in heavy stars. But there are other events. We have not talked actually about the fact how we can make gold, which could be in the aftermath of a supernova, but people also speculate, and maybe they're right, that this can happen in a completely different environment. If a supernova, a collapse supernova appears, then there is a rest of it, and this is called a neutron star. And if two neutron stars are actually close together in what is called a binary system, they can merge after long times into one system, which is a very specific, spectacular event, which creates a lot of neutrons. And this is also an environment which can make actually heavy elements, up to uranium and thorium, and also gold. We have to test these kind of theories, and we have to test them in two ways. Of course, there is a lot of astronomical observation, and if we want to have a real serious science, then our models have to reproduce what we observe. And what we observe means that if you have a supernova explosion, we actually know by which elements are being produced. We know actually also with which velocity they are probably flying apart. So all the models have to match this, otherwise there's something wrong with the model. And then we come to the second important step, having all these facts. Then of course you ask the question, do we know the nuclear physics, which goes in, because we just talked about the fact that astrophysics is applied nuclear physics. So then we have to learn about nuclear physics, and then there come two aspects into the game. The one is we have to measure the basic properties of the nuclei which occur in these astrophysical events, which is actually not a trivial question. And then unfortunately in the laboratory we can create these nuclei under certain conditions, but usually not under the extreme conditions of these hot temperatures and densities as they are in stars. So we need then a second step, which is nuclear theory. And both steps are very important, and both steps we are doing at the, we are basically at the eve of a new era in nuclear astrophysics, because we are building at the moment facilities worldwide in which we can produce, very often for the first time, those nuclei which we think are important in supernovae, for example. So these are so-called radioactive ion beam facilities, where you need very high energetic reactions to produce rare elements far away from stability. And then, of course, you need very important devices to study these nuclei, because you also need the properties. And then you need nuclear theory to take these data and combine it and use it. I have to say that Spain plays an important role on both aspects. I mean, you do not have the facility here in the country, but the Spanish groups from various universities actually play a forefront role in many of the laboratories, at least in Europe, but also outside. And they build forefront detector equipment which you need. So there is the accelerator, there's one in my home place in Darmstadt, there's another one in France, there is one in Geneva, but there are also some in Japan and in the United States and in Canada. But they are not sufficient. I mean, you produce the elements, but if you want to learn about the properties, you need high technology devices, and some of them are being built here in Spain. And then they are transported to do the experiments, and that means that this is an international collaboration where Spain has a high visibility. And then comes the second step, and this is the other strength in Spain. You have to learn from these experimental facts, and then you need your theoretical understanding to translate them into what you lose in stars. And there are also quite a few groups in Spain which do two things there. They transform the nuclear physics, they try to understand the basic nuclear physics, transform them into what you need in nuclear astrophysics, and then you have the modelers which develop the astrophysical models. And that's, of course, then the marriage you need. And this happens in Barcelona, this happens in Valencia, this happens in Madrid, in Santiago. You have them at several places.